Today we're going to continue talking about the interval of convergence, figuring out where a power series converges. Yesterday we had these two examples, and the focus here was on where's the center. For a power series, we can always get convergence at the center. We plug in the center of the series, that zeroes out all the terms, and the sum of infinite zeros is still zero. Notice that when we're just looking at x to the n or x minus 4 to the n, we can see where the center was. That was one of the things that we wanted to point out with these two examples. But we also saw this x to the n part. That's giving us our radius. Because we're thinking about running things through the ratio test. And once I plug in a value for x, this x to the n factor is an exponential factor. It's going to leave behind an x in the limit from the ratio test. So the limit from the ratio test tells us the series converges if the limit from the ratio test is less than 1. When we looked at these and ran them through the ratio test, the limit from the ratio test was just absolute value x. In the second one, the limit from the ratio test was absolute value x minus 4. And the ratio test says convergence if the limit from the ratio test is strictly less than 1. So when we're looking at this x to the n part, we're imagining that to be exponential in n. That's going to help determine our radius of convergence. The things that we wanted to think about. The things that we wanted to think about as far as factors that we look for when we're doing a ratio test. Polynomial and radical factors, exponential factors, factorial factors. Because of the way those those interact, which ones dominate over the others, each one will tell us something about the interval of convergence. The polynomial or radical factors only matter at the endpoints. The polynomial or radical factors only matter at the endpoints. The exponential factors will contribute to a finite radius of convergence. Exponential factors, when you run them through the ratio test, leave behind their base. So if the limit just goes to 1 because everything else is polynomial factors, then the exponential factors are contributing to the finite radius of convergence. Because exponential factors, when you run them through the ratio test, leave behind their base. And the factorial factors may contribute to a 0 or infinite radius of convergence. Factorial factors, when you run them through the ratio test, leave behind n's that are not balanced by the same degree n, like with polynomial factors. So let's do some more examples. I want to start by looking at the exponential factors contributing to the finite radius of convergence and how we can deal, how that will show up. So I'm going to take the examples that we had before, and I'm going to throw in additional exponential factors. So for example, let's suppose that we have the sum. N goes from 0 to infinity of x to the n divided by 2 to the n. The skill we want to develop is to think, what's the interval or the limit from the ratio test going to be? In this case, it's going to be the absolute value of x over 2. The ratio test says that that series converges if the limit from the ratio test is less than 1. So if the absolute value of x minus 2 is less than 1, that means the absolute value of x needs to be less than 2. The 2 in the denominator changes our radius. We multiplied the radius by 2. Let's see the ratio test on this. Take the limit as n goes to infinity of the absolute value of an plus 1 divided by an, or times 1 over an. After all the canceling happens, there are no more n's. So the limit is the absolute value of x to the n, sorry, the n's cancel. So the limit is the absolute value of x over 2. And the ratio test says the series converges if the limit from the ratio test is less than 1. We're doing a ratio test. It's going to end up with a variable. Multiply both sides by 2, and x has to be less than 2 in absolute value. This is everything between -2 and 2. So our center is still 0. And we'll get everything strictly between -2 and 2. We have to check the endpoints, but the same thing happens here when we check the endpoints. If x is 2, then we get the series, a sum of ones, which diverges. And if x equals -2, then we get the series -2 to the n over 2 to the n, or a sum of -1 to the n, which also diverges. So the endpoints are not in the interval of convergence. We're looking at factorial, exponential, polynomial. We're looking at numerator and denominator. That x to the n is giving us our baseline interval of convergence. Absolute value of x is less than 1. That 2 in the denominator means x can go all the way up to 2, because then it gets divided by 2 to the n. Gets divided by the 2 and becomes less than 1. So we care about numerator versus denominator. What would change here? I've taken the 2 to the n and moved it from the denominator up to the numerator. X to the n, that gives us our baseline. Absolute value of x should be less than 1. But the limit from the ratio test, if you just think about what the limit from the ratio test is, it's going to leave behind this exponential factor, absolute value of 2x. We solve that for x, we'll divide by 2, and the absolute value of x should be less than a half. So we should immediately think the limit from the ratio test. Series converges if the limit from the ratio test is less than 1. And that means the absolute value of x should be less than 1/2. Everything in within 1/2 of 0. Picture it. Even though our radius of convergence has been changing, you may notice that I'm drawing the same picture. Because all this interval is going to be, since there are no factorials to give us all real numbers or 0, there's going to be a center and some finite radius. If we look at the endpoints, we see the same thing happens, because this is all exponential in n. So when x is equal to -1/2, then our series is going to be 2 to the n times 1/2 to the n, which is the series of 1, which diverges. And when x is -1/2, then we get the series 2 to the n times -1/2 to the n. We just get this alternating 1 minus 1 plus 1 minus 1. I spelled D very 80s computer style. What we want to be able to do is read a center and a radius from the exponential stuff. All we have is exponential stuff here, exponential stuff in n. The limit from the ratio test is going to be absolute value of x minus 4 over 2. To solve for x, multiply everything by 2. So we expect our interval of convergence to be absolute value of x minus 4 has to be less than 2. We're also going to notice that there's no polynomial stuff in n. So the ratio test is going to come up 1 at the endpoints. So we can read that the endpoints are not included. And we've just taken our center, moved it to 4, but now we have a radius of 2, all the way up to 6 and down to 2. So we can read what the interval of convergence is right away without running a ratio test and doing all that work. Okay. So the interval correct. If we plug anything from between 2 and 6 into our power series, we get a convergent power series. Yeah. Because if I plug in, say, 5 minus 4 is going to be 1, so our series is 1/2 to the n. So it's convergent geometric. But if I plug in, say, 1, I get 1 minus 4 is negative 3 to the n over 2 to the n. And so the limit from the ratio test is going to be 3/2, which is greater than 1. We should check the endpoints. And what we're going to find is exactly what we found before. When all we have is exponential stuff, the ratio test is not going to be able to see what's going on at the endpoint. So let's see that happen. If x is equal to 6, then our series becomes 6 minus 4 to the n over 2 to the n, which is a 2 to the n over 2 to the n. So the power series diverges at x equals 6. If we look at the series 2 minus 4 to the n over 2 to the n is going to give us the alternating. So we get negative 2 to the n over 2 to the n, a sum of negative alternating ones. So we check the endpoint because the ratio test does not see what's going on at the endpoints. The n doesn't get canceled out because of the basis. I get a 2 to the n divided by a 2 to the n. Those n's cancel out, but I'm still left with a minus 1 to the n. So it would look like we have negative 2 to the n. That's a negative 1 to the n times a 2 to the n. So the n's aren't getting canceled out. A 2 to the n gets canceled out, but this n is still there. So the ratio test can't read what's going on at the endpoints. That's why we have to keep checking the endpoints. But since we're so fast at reading whether a series converges, we can just imagine what's going to happen. We see with all the exponential stuff, it's going to end up to be a sum of 1 or a sum of negative 1 to the n or a negative 1 to the n, both of which diverge. Or sorry, both of which diverge. So the endpoints are only going to change things up if we have some polynomial factors, because polynomial factors determine what's going on at the endpoints. So let's take a series that we know. And let's throw in some exponent or polynomial stuff. I'm going to put n plus 1 squared so that I can still start at 0. Not that it makes a difference, but I'm going to take that n squared and push it into the denominator. And then if I have n squared in the denominator, I can't use 0. I don't want to see anything too fishy. So if we think about the ratio test is ignoring this polynomial and just cares about this exponential business. So in the ratio test, the limit from the ratio test is just going to be the absolute value of x minus 4 to the n. Or sorry, just x minus 4 over 2. The limit from the ratio test ignores the polynomial stuff. The limit from the ratio test, or sorry, the ratio test ignores the polynomial factor. So don't worry about the n plus 1 squared when I think about the ratio test. The polynomial stuff comes into play when we start checking the endpoints. Well, let's actually see this happening. If we use the ratio test, we'll take the limits as n goes to infinity of the absolute value of a n plus 1. So n plus 1 is n plus 2 squared, x minus 4 to the n plus 1. And then divide by n plus 1 squared, x minus 4 to the n. If we think about the stuff that's canceling, 2 to the n over 2 to the n plus 1 will leave behind a 1/2. And x minus 4 to the n plus 1 over x minus 4 to the n will leave an x minus 4 behind. Since all the n part cancels with the x minus 4 and the 2 to the n, we can take it out of the limit as n goes to infinity. I've got limit n goes to infinity of n plus 2 squared over n plus 1 squared. N squared over n squared, that limit goes to 1. Which is in action, the ratio test, ignoring the polynomial factor. The only important part in the ratio from the ratio test was the exponential stuff. The exponential stuff will dominate over the polynomial stuff. The ratio test is ignoring this polynomial stuff anyway. Since we've got polynomial stuff, though, that might affect the endpoints. I mean, looking ahead, it's not gonna in this case, because both endpoints we're gonna get the divergence. But if the two endpoints are, let's see, in the middle we got 4, down at the bottom we've got a 2, and at the top we've got 6. So when x equals 6, when x equals 6, we end up with the 2 to the n over 2 to the n. That part cancels out. And we just have a series n plus 1 squared. Terms don't go to 0, so the series diverges at x equals 6. And at the other endpoint, we'll have 2 minus 4 to the n. This is where we're going to get the negative 1 to the n. And so our power series is going to diverge at 2 as well. We plug in one endpoint, we get 1 from the exponential stuff. We plug in the other endpoint, we get alternating from the exponential stuff. Note that in this case, this series is alternating, but that doesn't matter because the terms don't go to 0. So we don't actually care that this series down here alternates. The limit of the term is 0. That means our endpoints are not included. Questions? What you need to write down for this is here, not this part, just the part in the box. The skill, when you know how to do this, when you don't have to write down the ratio test, when you don't have to write down checking the endpoints. You just look at the power series and say the exponential part's center is at 4, 2 in the denominator means the radius is 2. Absolute x minus 4 is less than 2. The endpoints, we have an n squared, so that's going to diverge at both ends. Making that alternate doesn't help. All that should be taking place just thinking about it, reading what's going on, and coming to this conclusion quickly. The point of being in math classes is not to learn how to write this every single time, but to learn how to read what's going on because you know what's going to end up in the writing down. What we're trying to develop is a skill to read what's going to happen in this power series so that we don't have to do the ratio test. So here's how the read would go. The center is at -4, or sorry, the center is at 4 from this x minus 4. Since there's a 2 to the n in the denominator and no other factorials, it looks like we're going to have a radius of 2. And since there's an n squared in the denominator, one endpoint will have a 1 over n squared that converges. And at the other endpoint, we'll have an alternating 1 over n squared, which also converges. Here, the endpoints are going to be included. So we would say that this is absolute value of x minus 4 is less than or equal to 2. We're drawing it. In the center, we have a 4. At the bottom, we have a 2. At the top, we have a 6. And we put a square bracket to indicate we want to include 2 and 6 in the interval of convergence. The R included part means or equal to. Since the endpoints are included, the point is we want to know what's going to happen in the ratio test so we don't have to run the ratio test. We want to know what's going to happen when we check the endpoint so we don't have to write down checking the endpoint. But we're going to check the run the ratio test and check the endpoints anyway because we're new. And we see all these familiar things happen. The x minus 4 to the n plus 1 is divided by x minus 4 to the n. It leaves behind an absolute value of x minus 4. Two to the n over 2 to the n plus 1 will leave behind a 1/2. There's our limit from the ratio test because the ratio test is going to ignore all this polynomial business. There's our limit from the ratio test, just like we had predicted. Absolute x minus 4 over 2. And if we check the endpoints at 6, we get the series 6 minus 4 to the n over 2 to the n times n plus 1 squared. So we get convergence when x equals 6. Absolute convergence, I guess we should be more specific. Because 1 over n plus 1 squared is always positive, so we get absolute convergence by default. Not because we're doing a ratio test, because we're not doing a ratio test on the endpoints. Here's where we're going to get the alternating, and it's not going to matter because we have an n squared in the denominator. In this case, both endpoints are included in the interval of convergence. Questions? So I've got one more change to make. I'm still going to use this x minus 4 and the 2 to the n in the denominator. But I'm going to change out my n plus 1 squared. I'm not going to use an n squared. We're just going to use, let's say, a square root. So when we look at this power series, we see our familiar exponential in n stuff, the x minus 4 to the n over 2 to the n. That's going to be our limit from the ratio test because the ratio test is going to ignore this square root of n plus 1. So we're going to start by thinking about the absolute value of x minus 4 should be less than 2. So our center is still at 4. Our lower end is still 2, and the upper end is 6. We're definitely getting everything in between 2 and 6. What we're going to find in this case is that since our series, when I cancel out the exponential stuff, our series is going to be 1 over square root of n, which diverges. Unless it's alternating, in which case it will be conditionally convergent. What we're going to see is that 6, just like in the previous examples, is going to leave behind a 1 to the n. That won't help us. So we'll have divergence at 6. 6 is not included. But when I plug in 2, that's when I get the alternating. And I'll have an alternating 1 over n squared, 1 over square root of n. And that will give us conditional convergence. Conditional convergence is still convergent. So 2 is included. So I don't get to use absolute value inequalities. I could say 2 is less than or equal to x, but strictly less than 6. At the 6th end of our interval of convergence, we plug 6 in, we get the series 1 over square root n, which diverges. P series comparison with p series, where p is equal to 1/2. On the 2 end of the interval of convergence, when I plug the 2 in, I get an alternating 1 over square root of n, which is conditionally convergent. So at x equals 6, we get the series 1 over square root n, that's divergent. And when I plug in t, we'll get the alternating version, because that's what the exponential stuff does when we plug in the endpoints. It gives us 1 to the n or negative 1 to the n. So we get divergence at one endpoint and conditional convergence at the other endpoint. Don't forget to practice running the ratio test. You want to see for yourself the ratio test ignoring this square root of n plus 1. Any questions? Know where to find the center. Know what to look for any finite interval of finite radius of convergence. Know what's going to happen at the endpoints. Know what you have to look at to determine each of those things. Center, radius, endpoints. The part that we haven't included, the thing that we have not seen, is a radius of convergence of 0 or a radius of convergence at infinity. So that would mean the power series that only converges at the center or converges for all real numbers. The third thing that we're on the lookout for when we're running ratio tests is factorials. So you can probably guess what's going to be happening tomorrow. We're going to be dropping in some factorials in our power series and watching how the ratio test goes to 0 or goes to infinity. Because factorials in the ratio test leave behind n's in the numerator or denominator. Any questions? All right. So, oh man, spoiler alert, I just told you what we're going to be doing tomorrow. Oh, that's okay. This is math class, not a movie. So we're good. You don't get to complain about spoilers. All right, that's it for today. I'll see y'all on tomorrow, but have a good day and thanks for playing.